Okay, so we are live. We can start now.
Good evening, everyone. I, Shivangi, on behalf of Society for Data Science, BIT Mesra, welcomes you all for our today's session. As you know, we, Society for Data Science, strives to be the single focal point of overall development and growth of the student community with interest in areas of data science, data analytics, machine learning, big data. We are delighted to host Data Science Summit 2022 in collaboration with DPhi. In today's session, we are having Mr. Dipanjan Sarkar sir with us, who is lead data scientist at SIT Academy and honored with Top 10 Data Scientist in India 2020, and also a Google developer expert in machine learning, AI advisor and consultant at Springboard, and data science advisor and consultant at Analytics Vidya. Today, he will be sharing the insights about artificial intelligence and its role in the industry. Over to you, sir.
Thanks for the introduction. And yeah, hi everyone. Thank you for having me here. Let me bring up my presentation and then we'll get going. Let's see. Okay, so hopefully the presentation is visible. So now we'll talk about what is the role of AI in the industry. What I mean by that is you might have heard a lot about artificial intelligence in terms of both how it has been hyped up as well as maybe that AI can't do much in the real world. Today's presentation from my side is nothing to do with the hype about AI or claims like AI is making killer robots and all that. All I want to show you is if you want to break into a career in data, break into a career in machine learning or deep learning or artificial intelligence for that matter, what are some of the problems which you can solve in the industry? I will show you very different problems from each other, and that will show you the diversity of problems which are out there in the industry. Okay, so this is how the session agenda is going to be structured. Considering this is a like a super technical presentation, which I usually do, I will, considering the audience also, I will not go super deep into the technical details so that you don't lose interest. But what I'll do is I'll cover some of the background information also you need to understand the use cases which I'll be presenting. So I will start with talking about learning basics so you understand why do we care about learning or what do we mean by learning itself. Then I'll go into neural networks in terms of what is known as deep learning or why is deep learning become so effective in the recent several years. Then I'll talk about transfer learning, which is a slightly newer concept, not that new, it's been there for several years now, but you will understand what is transfer learning all about. And we'll talk about a few of the popular neural network model architectures out there, which are extensively used for deep learning. And then we'll go into all the use cases. And as you can see, I have a total of 6 use cases here. And based on the names, you can see they are like super different from each other. We have something about predicting failures in data centers. We have a use case in healthcare domain, like can you detect malaria? Can you predict whether your system or your application has some security vulnerabilities? Super resolution of images, which means improving the resolution of images. Style transfer is more around the aspect of applying filters on images and kind of stylizing the image. And the last one is finding out if there are anomalies occurring in your infrastructure at work, could be in manufacturing devices, could be in your own computer. So as you can see, like they are very different from each other. Some have to do something with images, some have to do something with predictions, some have something to do with image generation, and so on. Okay, so let's talk about the basics of learning. Why do we need learning, or what is learning? So, the reason why we need learning is we as humans have this thing called the brain, and it has been continuously inculcating information right from your birth, right? Since you were born, you have been seeing a variety of things around you. You have been learning a variety of things around you, and you have been retaining that information. Of course, you forget some things over time, that is there, but you retain a lot of things over time, right? If I say that, can you find out the chihuahua or the muffin from here, right? The dog or the muffin from here? You can immediately get the idea that, yeah, this is probably a dog, this is a dog, this is a dog. Now, how do you know that? You have retained that information since you were a child, that a dog will probably have two eyes, it will have some kind of a nose in this position, it may or may not have whiskers in this position, and it will have a mouth. But the computer doesn't know that. The computer literally has no idea how does a chocolate chip or a blueberry muffin look like, or how does a dog look like. Same thing in this problem on the left side. There is a dog called a sheep dog, which actually looks like a mop. But you know for sure that based on the nose, the tongue, or the mouth, as well as maybe they will have some legs, you can distinguish it even without having the background information about a sheepdog. So, in that way, the point here is that humans are intelligent, machines are not. The humans are the people who make the machines intelligent by feeding it data, by feeding it information, and then training it and trying to make it get better and better. And that's the reason why we need learning. The reason why we need learning is we want to automate increasingly complex tasks, because we can't have a human sit and distinguish these photos every day, right? We can't have a human sit and label pieces of information every day. There are many more important tasks to be done. So, because in today's day and age, we want to automate so many tasks, we want to automate a lot of things to make our lives easier. That's the reason we need learning in the context of machines. The other reason, as I said, is we as humans are typically built in such a way, thanks to our brain, that we can automatically start discovering, inspecting, comprehending patterns thanks to our brain. Like, even before I could give you an idea about these images, probably you already started thinking in your brain that, yeah, this is a dog, this is a muffin, and probably the task here is to distinguish them, even before I told you. Because that is how we are. We automatically start finding patterns and we automatically start thinking things. Now, automatically doing this is the heart of most useful applications out there, some of which we'll be covering today from a case study perspective, like image recognition, object detection, natural language processing, speech processing, robotics, and so on. Traditional programming is what a lot of you may have learned from a software engineering standpoint, where you have some fixed inputs, you have some kind of application you will build, and you will showcase some results, right? Like just like our tax computation, there are some fixed rules. If you earn more than this much, you will have to pay this much tax. So you just follow that fixed logic and you build an application. But what if you have some kind of a problem just like this one, or you have some kind of a problem like, let's say, a simple prediction of, can I predict the price of a house given the different features of a house, like the square feet area of the house, the number of bedrooms, and so on. It's not like you can literally go through every house measurement and build some if else rules. It's impossible to do that. It is not scalable. That is where the idea is, can we leverage these algorithms which are data driven, so that you can feed it your data, you can feed it your objective, and it helps in automatically learning those patterns. And that is known as data driven learning. And to be more specific, there are different aspects of that, which include machine learning, deep learning, and so on. So ultimately, the objective, what we are trying to do in the real world nowadays with AI, is making machines learn by extracting useful, meaningful information from the underlying data. Meaning is known as semantics. And of course, we need models to learn from data, typically a lot of data if possible. And more than a lot of data, it should be good quality data. If you have millions of rows of data and they are bad quality, nothing is going to be learned by the model. This is one of the most common slides, but a good slide if you're trying to get into data science or machine learning and so on. So, what is artificial intelligence? Artificial intelligence is any kind of an intelligent system which has been built in such a way that it can mimic or perform increasingly complex human level intelligence tasks, leveraging some kind of data driven intelligence inside it. Okay, so for example, when you open up your Google Translate and type in a sentence in English, and let's say it gets translated into Hindi, that is known as language translation, which is actually an increasingly complex task. It is not a super easy task. Okay, so that is an AI system. When you are talking to your phone using a voice assistant like a Siri or a Google Assistant, what will happen is it will also recognize your audio data, it will recognize your speech, it will translate it into text, it will run some kind of a search query, and then it will give you back the answer typically by showing it to you or speaking it back. So that is known as like a speech to text to speech system. Okay, so that is also a human level task. It is just like a human talking back to you. So that is an AI system. Now, how do we power these AI systems? You power these AI systems by using data driven models or data driven algorithms, which can increasingly get better and better as you start feeding it more and more data. So, at the heart of any AI system, you will typically have some kind of a machine learning model. And a machine learning model is basically nothing but a mathematical function which can learn patterns from underlying data to perform some kind of a task like predictions, extracting insights, grouping things together, finding out similar items, and so on. And deep learning is also machine learning to an extent, in terms of that deep learning is a very specialized field of machine learning algorithms which leverage only neural networks to solve problems. Okay, so deep learning is a special class of machine learning models, which are neural networks. And these neural networks have multiple layers. Sometimes they are often super big models, and that is why they are known as deep neural networks. And they tend to perform better with larger data sets, with images, text, audio, video, and so on. What are some of the types of machine learning? The most common categories of machine learning include supervised, unsupervised, and reinforcement learning. So, supervised learning is basically where you have already labeled data, like the house price example I talked to you about, where given the different features of a house, I know the price of a house. That is my historical data. So, the model can learn relationships between the attributes of a house and the price, so that in the future, if you give it a new house measurements, a new house attributes, it will be able to predict the price of a house. If you don't have label data, that is where you might need to think of unsupervised learning. Most common example is customer segmentation, where given different attributes about the customer, like how frequently are they purchasing items in a store, maybe like an e-commerce store, what is the total amount of money they are spending maybe every week, when was the last time they purchased an item, what kind of items are they purchasing. Based on those kind of attributes about a customer's behavior, can we group similar customers together? And that is known as customer segmentation. Typically we use unsupervised models like clustering to achieve that objective. Remember, in case of unsupervised learning, we don't have any labeled data like the price of a house. We only have attributes or features about our data set. And reinforcement learning is more of like a, you can think of it as like a dynamic learning system where it will have some kind of an agent which it tries to make intelligent by looking at the environment around it. And the agent will make some decisions, like it will move in a certain direction or it will make a certain action. and then you will reward or penalize that action based on whether it is making the right decision or not, just like playing a chess game. So the chess board is the environment, and the computer playing chess, that is the agent. And based on this reward penalty system, you keep improving that agent, and that is known as a reinforcement learning system, where the model is training the agent to continuously learn from mistakes. In terms of neural networks draw their inspiration from the neurons in our brain, neurons and axons in our brain. Neural networks are nowhere near to our human brain. So often in many literature or other places, you might see that the neural networks are the replica of the human brain or something like that. And that is where we need to make sure that we are correct in the way of we understand what neural networks are. Okay, so neural networks are just an inspiration of an artificial construct which is trying to emulate the brain, but it is nowhere near that. Otherwise, we would have reached human level intelligence by now. So it's basically like a simulation of how neurons work in our brain, where we have some inputs coming in the form of features. We will have some kind of a mathematical operation here where we will combine these inputs. We will pass it through some nonlinear activation functions so that we can learn some nonlinear patterns in the data. And then this output gets passed into maybe another neuron or another layer with a lot of neurons and so on. So training of neural networks is pretty straightforward. You will start off with some data. You will pass it through the neural network where you may have multiple neurons or multiple layers with multiple neurons. You will get the prediction at the end of the network. You will compare the prediction with the actual values. Like if you're doing house price prediction, you'll compare the predicted price with the actual price. You will compute the error. That error is known as the loss. Then what you will do is you will take a differential of that loss with respect to each layer from back to front. Okay, so that differentiation gives you the gradient of the error or the gradient of the loss. And then you will update the weights of every layer with the gradient. And the idea is to continuously keep doing that till the weights of these neurons in the layers become adapted in such a way that they are able to figure out the underlying patterns in your data and give you an accurate prediction. Deep learning is often known as machine learning on steroids, especially in the case of text, audio, video, and so on, because you don't need to sit and always manually extract features. You can pass the data after some pre-processing directly into the model, and it can take care of things like automatically extracting features and performing the task like a classification or detection, segmentation, and so on. So you can save some valuable time in which can get wasted if you're manually extracting features. Again, this is not super applicable for tabular data. If you are having like Excel data and so on, that is where machine learning models often outperform. But for images, text, typically unstructured data, these models perform pretty well. In terms of the terminology, again, if you have just one layer of neurons, that is a one layer neural network. One neuron is just a simple logistic regression model. And if you have more than 3 or 4 layers of neurons, that is known as a deep neural network. So why are we talking about deep learning, or why has deep learning become so effective in the recent several years? The reason is that the adoption of deep learning across multiple industries have been massive. Not just deep learning, even machine learning for that matter. So if you can see in consumer applications like assistants, chatbots, personalized search, augmented reality, a lot of applications with regard to AI. Same thing with healthcare. You have, just like I said, the malaria detection. So can I detect a COVID from an X-ray scan? So medical imaging problems, drug discovery, patient health record processing, a lot of applications in healthcare, finance. We have a lot of algo trading models out there these days. detecting fraudulent transactions. Okay, so mitigating risk, some of the very popular applications. Retail, a lot of stuff like customer segmentation, customer loyalty programs, supply chain optimization, marketing, targeted marketing, advertising. And again, possibilities are endless. We have a lot of stuff in government, energy, transport, industrial, and you can see IT services, media, space, sports. Sports analytics has become super popular these days. Analytics in gaming, education. So all this slide is trying to tell you is the whole point of my presentation, that AI has propagated almost every industry. And if you are interested in this field, you can actually get to do a lot of interesting problems based on domains of your interest, if you target that domain, that is. So don't believe in all the hype, but focus on real world problems, and you will get to learn a lot. You will get to do a lot. How is deep learning effective? So, like I said, if you are doing machine learning, often you have to spend a lot of time in extracting features from the raw or the preprocessed data. But in case of deep learning, often you can skip this step because the model itself can help you in extracting features. Typically, it works best for text or image based problems. By image, I mean image, video, as well as audio. Okay, so typically a neural network is a multi-layer neural network, and each layer can help you also, depending on the type of layer. Like if it's a convolution layer, it can help you in extracting features automatically instead of you sitting and worrying about should I extract edges from the image or whatever, like a pattern from the image, a nose from the image, or some kind of a texture from the image. You don't need to worry about all that. The model will do it for you. Same thing with the best part about deep learning is it can seamlessly work with data of different modalities like audio, video, text, and so on. Like here, the speech is processed in the form of an image, then we pass it through a sequential model like a recurrent neural network, and then we extract or translate it into text. Okay, so that is where you have a variety of neural network architectures available, which can help you in solving complex problems related to speech, audio, text, video, and so on. In terms of neural networks, often bigger and more complex architectures can actually give you a better performance. That is why every year you will see some other research being released where the models are actually increasing in terms of their complexity as well as their size. They can also learn from less data, assuming your data quality is good. That is where you can use principles like transfer learning. And the toughest problems like understanding text, video, classification, segmentation, all of that are tackled by deep learning models. You can't use machine learning in most cases because it will not scale. Why we care about deep learning now? Because it has become very effective now. We are getting a lot of new algorithms from state of the art research models available to us within a few days after the paper is released, because people usually open source it. We have a lot more data available now. Several decades back, even if we had neural networks, we didn't have that much useful data available. Most important part, we have a lot of open source tools available to us now, like PyTorch, TensorFlow, and so on. And most important thing, you have faster compute, which is not super expensive now. So you can avail GPUs in the cloud, pay less than $1 an hour, and you can get going, right, and train these models on gigabytes of data. So that is where the best part is, that you have really good infrastructure available now. Several decades back, parallel computing was not possible on GPUs. It wasn't at that level as it is today. So it would take forever to train even a simple neural network. But now, within a few seconds, you can train a complex speech processing model or fine tune it, basically. What is transfer learning? Transfer learning is utilizing prior knowledge to apply to newer tasks. Like if you know how to ride a bike, it'll be easier for you to learn how to ride a car. If you know how to play a specific type of piano, playing a different instrument wouldn't be super difficult in that domain. If you know math and stats well, understanding machine learning becomes easier for you because you can use the prior knowledge. Okay, so traditional learning is where every task is solved separately. But in transfer learning, what happens is when you solve a problem on a given data set, can you use some knowledge from that problem and apply it and make your model better in the next task? And applying that knowledge typically means using the weights of a neural network, using the weights of a neural network model, when your model has been optimized and trained in the first problem, you pick that model and adapt the weights of the neurons of that model to your own new problem. So that is transfer learning. There are a lot of pre-trained models available nowadays. These are the models from a computer vision perspective. Of course, there are many more new models which have come out, like transformers and so on. The idea here is that the pre-trained models have been trained on a huge amount of data. They have been specialized um, to perform on tasks like classification, and you can then fine tune them to solve classification, segmentation, object detection, and many more tasks. You can use them to extract only features. You can even use them to extract features as well as solve your objective, like whether it's a prediction or segmentation and so on. A lot of pre-trained models are available for both computer vision as well as natural language processing tasks. These are a lot of the popular models, if you remember, for NLP tasks. So it's not like we have only pre-trained models in computer vision. Nowadays, you have a lot of pre-trained models available even for natural language processing. Some popular deep learning model architectures. I won't go too deep into this, but just so you get an idea, we have convolution neural networks which can work with images as well as text. We have sequential models which can process like a sequence of words and make some kind of analysis or prediction. It can even process any sequential information, like it can process sequential time series data to predict, let's say, the next day's stock price. So those sequential models are typically like a recurrent neural network. A better version of recurrent neural network is the LSTM, long short-term memory network. A gated recurrent unit is faster than LSTM, but it's better than RNN. You can process a sequence of information in both forward and backward fashion together. Those are known as the bidirectional LSTMs or GRUs. You can use autoencoders to find out anomalies in your data, so very useful. Encoder decoder models are the most popular models these days, where you can process a sequence of data in the encoder and output a sequence of data in the decoder. Just like the language translation model, process a sequence of data in English and translate it to Hindi. Process your speech in the encoder and translate it to text in the decoder. So any of these newer problems are being modeled on this encoder decoder architecture. And if you use multiple encoder decoders, like a stacked layer of encoder decoders, along with some other concepts like attention and so on, that is your transformer models. As you know, these are the recent models which have come out. Very complex in terms of the size, number of parameters, and the time to train, but very effective in a lot of problems in vision as well as text. So now we will get into the use cases, where I will cover one use case after another so that you get an idea of what was really done in this problem. So the first application is predicting data center device failures. As the name suggests, the key objective here is there are a bunch of data centers which are operating. Can we predict a failure for that data center before the failure actually happens? So it's a tough problem because the idea is not to predict a failure after it has happened, because then it is pointless, but can we predict the failure before it might actually happen? So let us understand the problem here. To understand the model, we need to understand what are infrastructure devices. So typically, your network devices like your routers, load balancers, and so on, as well as your data centers, which are your server racks. Those are your key infrastructure typically for any kind of an enterprise, right? In any kind of a company, basically. Those are the systems which will help you stay connected. Those are the systems which will help you process information, run your applications. Now, in most companies, a lot of these systems are reactive in nature, which means that the company gets to know about a failure only after it has already occurred, which means the failure occurs first, there is a downtime, and the teams will try to fix those failures, typically the operations teams. The idea here is that can we leverage some kind of historical data to predict these failures with a good lead time? That is the most important thing. Can we predict the failures which may occur in the future? The objective here is not to predict a failure after it has already occurred. So, what is the data which we had for this? We had historical device events data from a database for over 2 years plus. So, we had close to 3+ terabytes of data, which is actually huge. Now, what is this device events data? The device events data is like, if you consider any system, there will be a lot of events happening throughout the day. It could be that, okay, an application is starting, or it is making a record of the CPU utilization. It is making a record of the number of incoming connections to the system. It is making a record of which application is taking a long time to get scheduled or run, which application is erroring out. So a lot of events are actually captured in any system, be it a server, be it your own computer for that matter. Excuse me. And it will also capture failure events when it happens in that server, right, or that device. So our perspective was that can we use the historical events data along with the failures when it happened to build some kind of a data set where we have bad observations and good observations. So bad observation is going to consist of sequences of events which happened before a certain amount of time, after which the device went down, right, or the device failed. And a good or a normal window of events is basically like a sequence of events which occurred when the device was functioning normally. So you can already imagine where I'm getting at. I'm trying to build two different types of data. One is events which are occurring when the device is going to fail, and one is events which are occurring, time series events which are occurring when the device is functioning normally. The reason is I want to train a model to recognize some patterns from these events to figure out, okay, the device will perform normally when these kind of events are happening. The device will probably fail if these kind of events are happening. That is the gist of it. I want to build a model to learn that kind of patterns, because we manually can't go through 3 terabytes of data and build some if else rules. That will be foolish and that will be impossible. So that is where one of the deep learning approaches we took was build like a heat map of events where every event is on the y-axis, as you can see here, and your x-axis is a time. Like, okay, in a 6-hour time period, if we divide it into 5 minutes each, like 0 to 5 minutes is one slice here, 5 to 10 minutes is one slice here, 10 to 15 minutes is one slice here, and try to compute the frequency of the number of times each event occurred in that slice. So what will you get from this? From this, you will get that, okay, based on a sequence of 6 hours of information before a failure happened, you can get the full frequency map of how many events were occurring for each of the events over this time. So this process is known as converting your events data into a multivariate time series data. Why multivariate? Because you have multiple variables or multiple events. And time series because you have the frequency of the number of times these events are occurring over time. So you can imagine this as a two-dimensional matrix, right? Where you have events on the rows and the time on the columns, and the values are number of times each event is occurring. And this matrix can also be considered as an image if you think about it, right? Because it's just a matrix of pixel values where each pixel is the frequency. So the whole point here is the time series in each window is now a tensor or a matrix of these events occurring over time. So basically, this is like a heat map window, right? This window of data is like a heat map of all the events occurring in this time interval. So the idea is, can we, instead of trying to find out the patterns manually, just pass this to a convolution neural network and help it automatically figure out the patterns and then use it for classification of failure or not failure? And that's exactly what we did. We built our own custom convolution neural network here with multiple convolution layers and pooling layers. And then we did some classification at the end of it. The classification is basically that, is it going to lead to a failure, which means after these events have occurred in the next 6 hours, will there be a failure or not? Okay, so good or bad, trying to predict whether there will be a failure or not. So initially we started with building our own custom model with a lot of convolution and pooling layers, and later we tried some of the pre-trained models also, like a VGG or a ResNet and so on. And if you see here that these are where we had some manual features extracted. I can't reveal those features considering the sensitive nature of the project, but the idea is we tried a lot of machine learning models here. And you can see that the true positive prediction rate and the false positive rates are kind of given here to an extent. The idea is to reduce the false positive as much as possible and to improve the recall here as much as possible. And overall, you can see here that with the deep learning model, instead of worrying about extracting manual features, we just needed to transform our data in this format, and that's it. We got a really high performance as compared to rest of the models. Really low false positive rate and really high recall. Okay, so that is an example showing you like how these newer deep learning based models can actually be effective even on tabular data, considering you are formatting it in the right way and treating it as a image based problem, and then leveraging convolution neural networks for automatic feature extraction and then your classification. The next problem is completely a different problem in a completely different domain. Well, we have solved some healthcare problems, but we can't reveal those considering the sensitive nature of those projects. But this is based on showcasing to you that you can do a similar thing even on open data sets. So the malaria detection, there are a lot of data sets available out there from a bunch of research papers, which have actually thankfully open sourced the data. So the idea here is, okay, why do we care about this problem before we get into the solution? So as you all know, the impact of malaria is really serious in the tropical belt of the world, right? In the tropical belt of the world, especially like in South America, Africa, India, and other parts of Asia, because it is in a slightly hotter region. Malaria can be prevalent, where if an infected mosquito bites you, then parasites, if it is carrying parasite, it is not like if any mosquito bites you, you will get malaria, but if the mosquito is infected with certain parasites, those parasites can start destroying your red blood cells, oxygen carrying red blood cells, and you can get malaria. And if you are delayed in getting the right kind of treatment, then it'll affect your health basically. Now the idea is in cities we can get the at least a good treatment in a fast or a quick amount of time, but what about the rural areas like in villages and so on, where maybe a doctor visits them once a week or something like that, or maybe they don't have a proper hospital? So the idea here is that the process of detecting malaria is actually intensive, where you will need to take a blood smear in a slide. You'll need to scan that, magnify it, and get some domain experts to manually count the RBCs which contain parasites, and then say that, okay, probably this person has malaria. So it's an intensive manual process. Now the idea is, if we have these scans of the blood smear, right? The blood smear from the slide. If you have the scan and we have the outcome that, okay, this person had malaria. And we also have an outcome that, okay, probably this person didn't have malaria. Can we focus on building a model which can help us in detecting malaria, right? That is the whole point of it. So we have images which have a blood smear, and we have the outcome that, okay, they have malaria. And also we have the images which are again blood smears of different people who don't have malaria. So the idea is that we have these kind of scanned images which have been labeled. Like I said, models are not intelligent by itself. It's not like you just dump these images into the models and they will automatically start saying healthy or malaria. You need some prior labeled images of people who have already had malaria or didn't have malaria so that the model can learn from it. So basically, it is supervised learning. So that in the future, if you give it a new image, it can then, based on its learned information, it will say that, okay, yeah, probably this person is going to have malaria or not. So the methodology is pretty straightforward. You need a label data set of these cell images of healthy people as well as infected people. Otherwise, the model is not going to learn anything. You train the model on a certain amount of data, maybe do some validation and tuning, and then you check the performance maybe on some unseen data. You may need to pre-process your images if necessary, maybe do some data augmentation, like play around with the brightness or contrast, maybe rotate the images a little bit, especially if you have less data. And then you can play around with your modeling strategy, like you can build your own CNN models from scratch. You can take in a pre-trained model, use it to extract features, and then build your own classifier. Or you can even fine-tune your pre-trained model, like a model which has been trained on, let's say, some other data set like ImageNet, and then fine-tune it for your problem, and then check the performance. Okay, so this is a popular architecture which we tried out even in the previous, what do you call it, even in the previous problem. A lot of you might know it. VGG is built by the Visual Geometry Group in the University of Oxford. So it's a 19-layer network of convolution and pooling layers, followed by some fully connected layers. This model was originally used in the ImageNet competition. The ImageNet 1K competition is a competition to classify millions of images in 1,000 different classes. And that is where you will see that the last layer has 1,000 neurons to predict 1 out of 1,000 classes. So this model has already been trained on millions of images. And this model is already an expert in extracting features from images. But it may not be an expert in extracting features from images of your malaria data set. So that is where what we do is we remove these dense layers, the classification layers. We take only the feature extraction layers, the conv and the pool layers. These layers already have some optimized weights, right, through backpropagation, because it has been repeatedly trained to detect and extract features from images. And then what we do is we put in our own classification layers. Like maybe we put a dense layer of 128 neurons, and then we put a dense layer of 2 neurons to predict yes or no, like infected or not infected. And then we train this model on our data set, and we also fine tune or change the weights of these layers to adapt it to our problem so that it gets or it becomes an expert in extracting features from our malaria data. And based on that, these are some kind of performances you might observe that you can, assuming your data set is of good quality, you can easily reach an accuracy of over 95%, and in turn precision, recall, and so on. Okay, so the fine-tuned model gave us a precision of over 96%, which is pretty decent. If you try other models also, you will probably break the accuracy even beyond 98%. By accuracy, I mean precision, recall, and so on. Because you shouldn't just focus on accuracy, but especially on the precision and recall. Okay, so the idea here, what I'm trying to show you is you can use the same model in different problems. Like you can actually use this model even on the previous problem, where instead of taking the image of the malaria cell, sorry, the blood smear, you are taking the heat map of your events and you're passing it through this. And then you have your own classification layers to predict a failure or not failure. In this case, you are using a same architecture to predict whether person has malaria or not. Okay, so now we will head into a different problem in terms of this is, by the way, in an area of computer security. You can think of it as a cybersecurity problem, and this is like a completely different domain from what I've shown you so far. Okay, so this is a very different domain where people usually think, okay, maybe we can't really apply any data science to it, but actually you can do a lot. I see there are a lot of questions, so don't worry. We will have the Q&A session after the presentation once I finish showing you these use cases, and I'll try to answer as many questions as I can. So yeah, continue putting in the questions. We'll definitely come to each of them. Okay, so now coming to the next use case. The idea here is that we want to proactively find out vulnerabilities in the dependencies of your application. So let me explain what I mean by that. Let's say you're building a machine learning application. You will use some Python dependencies, right? Like you can use pandas, you can use scikit-learn, you can use maybe Flask or Fast API, and you build an application. Now you are just downloading those libraries and using them happily. But if you look at the vulnerability database, which is a database maintained by the government of the United States, you will see that some of these libraries often get really nasty, exploitable vulnerabilities through which hackers can do malicious attacks on your system. And these can include even popular libraries like TensorFlow, PyTorch, scikit-learn, and so on, which is a bit surprising if you think about it. But it's unintentional because, see, the developers of these libraries will be focused on pushing out features for all of you. But somewhere in the code, we have these people, right, who are always trying to hack into systems. They will be constantly trying to find out weaknesses in that code so that it can gain exploits in your systems. And the idea is, can we somehow predict those vulnerabilities that, okay, probably in your application, these are the ones which are having a high security vulnerability. So that is the objective of this problem here. Like I said, any developer, probably all of you are developers, you don't really code anything from scratch, right? If you want to load a data set, you will use pandas. You don't need to sit and manually write some code to do that. If you're doing it to learn, that's great, but in the real world, you focus on solving business problems. So that is where you depend on code or utilities already written by others, thanks to open source software, obviously. So what are these dependencies? They are open source or sometimes commercial reusable libraries, which all of us use. Each of these dependencies or libraries are focused on solving specific tasks. Like you have TensorFlow or Keras, which is used for neural networks. Pandas used for loading data, processing and aggregations. NumPy is used for numeric computations. And you have a lot of libraries, as you can see here, like some of these are for AWS operations, some of these are for Google Cloud operations, and so on. These are just some samples, by the way, sample libraries. The challenge with dependencies is every other day or month, some of the other new libraries coming up. And in some ecosystems, like in the Node ecosystem, Node.js ecosystem, NPM, the package manager, as you know, the dependencies have skyrocketed. You can see the growth is exponential. Okay, this is the year, by the way, and this is the number of dependencies. In case of Python, also it has increased. Of course, the growth is not as much as JavaScript, but it's pretty huge. So obviously, it is known that if more and more libraries are getting released, there is a high possibility of vulnerabilities also in those libraries. And that is the truth also. Based on some analysis done by this company, Snake, which is a security company, they have found out that over the years, the number of vulnerabilities have increased for any of these ecosystems, like the Python ecosystem, or the Golang ecosystem, or the Java ecosystem, that's Maven, and so on. Now, vulnerabilities, if they are not identified, they will be missed. Doesn't mean they are not present, just that they will not be disclosed publicly. And that is the biggest problem for the ecosystem we were tackling, that is the Golang ecosystem. A lot of you may have heard about tools like Kubernetes and so on. So we were targeting that ecosystem of products. And if you know that Kubernetes and so on, the source code of the actual engine is written in Golang, okay? The Go programming language, also known as Golang. So Golang is not as popular as the other languages if you think about it, right? Like Python is usually more popular. So that poses a bigger problem for us because less people work with actual Golang. They don't disclose a lot of these issues. By issues, I mean security vulnerabilities publicly because they never find it. But doesn't mean hackers doesn't know about it or don't know about it. They may know about it, but obviously they will not disclose it publicly because they want to gain access to systems. So that is where the idea is that can we somehow try to find those vulnerabilities? So the key objective here was to proactively predict probable vulnerabilities. We don't know whether it's definite or not, but the idea is there is a probability that, okay, there is a vulnerability in the direct libraries being used or the indirect libraries being used. Like if you install pandas, internally it needs NumPy. Okay, so NumPy is a transitive or independent, sorry, NumPy is a transitive or dependent dependency on pandas. Okay, so we want to find out if any vulnerabilities exist in this Kubernetes OpenShift ecosystem. Now, the good part is there is a lot of public data available using which we can find out vulnerabilities. Typically, as you can see, 48% of the time, someone opens a public issue about it, or someone sends a pull request, or someone mentions it in a code review in a pull request. And the good part about this, thankfully, is the entire Kubernetes ecosystem is on GitHub. Okay, it is not private code, so we can pull in the data from their GitHub code base and try to extract some useful information. I won't go into too much details about the model architectures and so on itself, because that itself can be like a session on its own. But I just want you to walk through this workflow so that you understand the scale of this problem. So what we do here is we pull in every day all the issues, all the pull requests, all the patch notes from 850 plus repositories on GitHub. Yes, the Kubernetes ecosystem is that huge. Like Kubernetes internally can use a bunch of other libraries, which themselves use a bunch of other libraries, and so on. Okay, so we pull in 850 plus repositories every day. What is the information we are pulling in? We are pulling in GitHub events. This includes pull requests, this includes issues, and this includes patch notes. We're pulling the text information, by the way. We pull in any discussions from mailing lists. There are a lot of public mailing lists discussing about issues of these libraries. We pull in information from Bugzilla. Bugzilla is a place where bugs are filed for these libraries. We store it in our data store. We process the information, the text information. We plug it into a couple of our models, which are typically sequential models like LSTMs or transformer models like BERT. And then we make a prediction that by looking at these events which are happening in this library, there is a likelihood that there is a vulnerability in this library on this date. And then we send it to our internal security team, They have connections with the creators of these libraries. Then they validate them, and then they tell us that these are your correct predictions, these are your wrong predictions. And of course, there will be wrong predictions because it's a model which will learn over time. It is not going to ever have 100% accuracy, but the idea is to get as close to it as possible. Okay, and then what we do is we keep updating our models with the correct information also and keep retraining the models. Okay, that is known as the triage feedback loop, where you get corrections of your predictions and then you retrain your model constantly. So internally, we have used transformer models. We started off with bidirectional recurrent neural networks, and then we moved on to transformers because they gave us a much, much better performance. Mostly we ended up using BERT. Not going into details of the transformer models today, but BERT stands for bidirectional encoder representation of transformers, which means use only the encoder blocks in the transformers, extract the bidirectional feature representations, and then plug them into a classification model to predict vulnerability or not vulnerable. So that's the workflow typically, like monitor 850 plus repositories, extract useful information like issues, pull requests, commits, even commits are there, I forgot. So we even pull in commits, patch notes, comments, conversations, pass it through the first model to, so we have actually a two-stage model as you saw here. Okay, so the first model will filter out events which are not related to security, because it's not like you have also worked on GitHub, you will put pull requests and so on, and you will file issues. It is not like every issue has something to do with security, right? Maybe out of 100 issues, 5 issues have something to do with security. So the first level of classification is classify whether a particular event is a security related event or not. Whichever is security, those are the few data points which go into the second model. Because every security event might not be a vulnerability. If you look at any of the open source libraries, you will see that sometimes they will say that, okay, improve the security using this feature in the library. So that issue has nothing to do with a vulnerability or a problem of that library. It is just the creator or someone, some open source contributor saying that, okay, add in this code to maybe add in this security feature. Okay, so we need to remove those, or rather we don't need to consider those, and we need to classify only the security events which are about vulnerabilities, which means like a serious exploitable vulnerability in that library. So that is what our second model specializes in. So our data set was focused on past 3 years worth of data. CV, by the way, is your security vulnerabilities, which are like serious in nature. Common vulnerability exposure, it's probably known as, if I'm not mistaken. It's been a while, but yeah, those are like your serious vulnerabilities. And as you can see, the data set is super imbalanced, using which we trained our data, the historical data. Like you had over 200,000 security events, but only 650 out of them are serious vulnerabilities. So these are the best performing models which we obtained, where you can see that the second model is the better performing model. Then, by the way, this performance is for this. Okay, this one performs very well. It is very easy to separate security from non-security. You'll easily get 99% accuracy or precision. Okay, it's not that difficult. But this is the most difficult thing. Inside security issues, which are vulnerabilities versus not vulnerabilities? That is the main challenge really in this problem. And here we tried different models, and the transformer model gave us the best performance, where you can see that 80% of probable vulnerabilities were correctly identified. And the precision is 71%. That is the best precision we got. For security and non-security, it is super easy. You can easily get a high score. This is the main challenge, okay? Finding out the vulnerabilities. So this is a problem, as you might have thought about by now, that it is actually very different from like regular problems. Because regular problems, you are already having a data set available to you more than often, and then you work on it. Here we had to literally scrape or crawl or use APIs to get information from public sources, process that data, store it, then build models on it. The entire project was done on public data. No one supplied us with any separate data. And that is how it runs on a day-to-day basis. Okay, last few use cases before we wrap up the session and go into the Q&A. Image super resolution. So the whole point of an image super resolution project is if you have a low resolution image, like let's say this box here you see, this low resolution image, can you expand it, magnify it into a larger image, but the pixels don't get messed up. You still get a high quality image, a high resolution image. What is the point of such a problem? You can leverage it for a lot of areas, like improving resolution of images for medical imaging, doing some surveillance, security, generating images to feed it into some other model, and so on. Okay, so super resolution model architectures. There are a variety of model architectures here. I won't be covering these in detail, given that we would really need to dive into the layers. But ultimately, it uses a combination of, as you can see, convolution layers, pooling layers, residual connections, dense layers, similar to some of the layers you saw in the previous models. Okay. So the popular architectures which can be used include residual dense network, residual inside residual dense network, which means multiple of these connected together, and the residual in residual dense networks with GANs. GAN, as you know, is typically generative adversarial networks, which have become very popular, especially in data generation problems. You can use GANs for synthetic data generation, so very useful. So the idea is you have your training data. Again, it's a supervised problem. To train a model to improve the resolution of an image, you need to show it low resolution image and the corresponding high resolution image so that it learns some features to understand how to scale the low resolution to the high resolution. Okay, it needs that kind of data. Again, like I said, there is nothing magical about AI. It's not like you just dump an image randomly into a model and it will magically magnify it. You need to train it to figure out what is the low resolution pixels, what is the corresponding high resolution pixels, and how can I learn the mapping. And you do it for maybe around, even here, you do it for around 2000 images. And you can use some loss functions like peak signal to noise ratio, which is basically like a pixel-wise mean squared error. This is a typical residual in residual dense network where you will have this kind of a block of multiple convolution layers with residual connections, and the same block will be repeated multiple times in the model. The whole idea here is having these structures will help you in removing the unnecessary, like bad shaped pixels when you blow up the image, basically. And this is an example which kind of shows you that what does it take to, like, what does it typically look like, where actually it's usually recommended you blow it up 2 times the size. Here we did it 4 to 8 times the size. And that is where you can see that it looks pretty decent versus, let's say, if you were to take this image and manually increase the size to 4 to 8 times. Okay, and there are a lot of other examples also, which we haven't shown here, but the whole point here is there is a lot of perspective where you can use different types of models, use generative adversarial networks, and gain even better quality images in a larger resolution. Neural style transfer is all about transferring the style of an image into another image so that it looks a bit artistic, like a painting and so on. A simple example here, you have this Taj Mahal image, you have a Van Gogh painting, you pass it to a neural network so that it takes the style of this painting and it colors up this Taj Mahal image, so that, as you can see in the style transferred image, you don't lose the structure of the content image, right? The monument remains as it is, just that it looks like it has been painted over by this style. That is what is known as neural style transfer, because you're using a neural network to do it. Main objective is to create artistic images of high quality. So it literally uses deep learning to apply the style of a reference image, known as the style image, into a target image, which is known as the content image. Okay, so at heart, neural style transfer is an optimization technique. It takes two images, like I said, a content image and a style image, and it tries to blend them together. Content image defines the overall structure and the higher level structural components of the image, like pillars, the trees, right? The dome structure here. Those shouldn't get affected too much. Like it shouldn't go away completely. That is the characteristics of the content image. Style is defined as like the painting style, maybe, or the image style in terms of the textures, the brush strokes, colors, patterns, and so on. And the blended image should look like exactly the content image, but it should be superimposed with the textures, colors, patterns of the style image. So here also you can use a pre-trained convolution model, convolution neural network, to extract the style from this image, extract the content representation, and generate a completely new image. That is the best part of it. This is not making a prediction of a value, but it is making a prediction of a complete image. Just like this problem also, it is actually predicting a complete image. By predicting, it's generating a complete image. Convolution neural network, again, the main focus in a convolution neural network is feature extraction. Using convolution filters and pooling layers, kind of enhance them by aggregating patches of pixels. Same model we have used here also, but you can play around with other models. So not going into details of this model again, but you can use the VGG model also to start with, because that's the simplest pre-trained model. Okay, so a given input image is represented as a set of filtered images at each processing stage in the convolution neural network. You can use specific layers in the convolution neural network model to extract the high-level content features of the content image. Like from here, you can use this. There is a block called block5conv2. Okay, this one. So you can use this layer to extract very effective content representations of the image. Similarly, you can use some other blocks to extract style representations and then kind of superimpose them with a loss function so that this image doesn't look super different from the generated image, as well as this image is also kind of similar to this image from a styling perspective. So you have like a style loss and a content loss. And these are some examples where you can kind of adapt a style into an image and completely change the way the image looks. Okay, last use case, infrastructure anomaly detection. So anomaly detection is a very common problem where, given some kind of a time series data, can we find out some extreme spikes, like someone is doing a denial of service attack into a company server, the number of connections will suddenly increase. So can you flag it immediately and block it using a firewall, something like that? So the model we used is known as a SHESD model, seasonal hybrid ESD model. It is not a super new model. It has been invented by Twitter in 2015. The idea is to remove any kind of seasonal pattern from the time series, repeatedly use a ESD test. ESD is nothing but a fancy t-test. ESD is known as extreme studentized deviate. So that is like a t-test repeatedly used in a recursive manner to find out outliers. So the whole idea is remove any kind of seasonal patterns and then identify anomalies in the remaining structure of the time series. Okay, so for each data point, we compute a G-score. G-score is known as a grub score, which is basically like a t-test score. Take the point with the highest score, and then based on your alpha value, which is your significance level, like a 0.05 or 0.01, we probably use like a 99% confidence interval because don't want to detect too many outliers or not have too many false positives. So if the score is greater, then basically the p-value becomes super low, and then you know that okay, it is an outlier. So it's a statistical model actually, and it performs very well as compared to a lot of machine learning based anomaly models like isolation forest and so on. This is actually like it shows you like a real world framework of how it has been built inside a company. You will get a bunch of sources of data here, like a temperature sensor data, CPU data, memory data, network throughput data. You can get log data, like what kind of errors are happening, what kind of warnings are happening. You can get application level data also. You will have some ETL loaders. This is typically the data engineering pipelines, which will store this data into Elasticsearch. Um, Actually, we store the data in Logstash. Elasticsearch is more of the interface. It'll be stored in a Elasticsearch index, if you think about it. Elasticsearch is like a NoSQL kind of a key value store, honestly. And then we pull in the data from here and apply different types of models. We have tried a lot of models, as you can see, like moving average models, concept drift, forecasting like ARIMA, threshold-based models, like if it goes beyond something, it's an anomaly. We have explored sequential models, temporal models, hidden Markov models. So this is how things happen typically in an industry. You try out different relevant models for the problem, and you try to see which one is not super complex, which one doesn't take forever to make a prediction, and which one gives you the least false positives. Because if you start mailing people thousands of anomalies, their solution is never going to be used. Okay, so that is where we have to be careful. Okay, so hopefully that brings me an end to the presentation part of today's session. Hopefully you got an. I mean, I could keep speaking for hours on more and more problems, but I don't want to keep all of you bored, especially on a Friday. So hopefully you got the idea, right? In terms of what does it take typically to solve these problems, what kind of models I use, what kind of techniques I use, as well as we covered completely different problems if you think about it, right? We started off with some data center predictions of failures. We went into healthcare. We went into cybersecurity. We went into image enhancement. We went into like building your own maybe paintings or applying filters to images. And we stopped with anomaly detection in infrastructure problems, right? So that is where the idea for you here was to get the perspective of what does it take to build these solutions, as well as what are the real world possibilities in the industry. That is the whole point of this talk, that AI can be hyped these days. A lot of people can say many things about AI, but the true AI is what you're seeing right now. Like these are real applications of applying. I don't like the term AI because it's a bit of a marketing term, but how you can apply like machine learning or deep learning and build these AI solutions for real world problems. Okay, so yeah, thanks a lot for listening to me. Maybe we can now do a brief Q&A session and go over some of the questions.
Thank you so much for sharing your thoughts with us, sir. Now we'll be having the questions come onto the screen and hopefully you can reply to them.
Sure.
Yeah, so the first one is, can you suggest some resources for us to learn deep learning?
Good question. Honestly, again, I don't want to bias you with my suggestions, but what I can tell you is there are a few books out there. You can start off by like using a reference book. So there is Deep Learning with Python, that is by Francois Chollet. So Deep Learning with Python is from Manning Publications. So do check out the second edition. The good part is he also open sources the code, so you can just search deep learning with Python GitHub. You can even check out the code. That is one good option. The other thing you can also do is deeplearning.ai has some courses, Andrewing, as you know, popularly on Coursera. So it's a good option because it doesn't have a super complicated learning curve. So even students can pick it up. So those would be my two things to start with. Okay, and then you can, by then you will get like you'll be experts enough to check out your own resources.
Okay, sir. I think everyone got that. Next, we have some suggestions for logical developers looking for transitioning into ML, looking for a transition.
Yeah, so software developers transition into ML. It depends on what you want to do. Like, if you are interested in the software engineering side of things, you can still be like a software engineer in machine learning, as it is known as, also known as a machine learning engineer. So, like in that case, your engineering skills will still be important. You can learn maybe a bit of how to work on the cloud, how to deploy models, how to scale up models, how to monitor models, how to retrain models, because those are the key tasks of a machine learning engineer or a software engineer in machine learning. Now, if you say that I don't like doing those things, I want to do data science, then you have to look at the skills you need to be a data scientist. So that is where you have to start with the basics, understand how to frame business problems as data science problems. That is something people skip because no one will tell you that predicting this one is a classification problem or this is, let's say, a clustering problem. You have to figure those things out. So one of the first things you have to start with is understanding how data science is being used in the business. Then next step is understand about data, understand different types of data, how to process different types of data, load different types of data. So that is where this is a skill which is often overlooked because most people say, yeah, start with statistics, read it for several months, then go into machine learning. It's not how the world works today. No one has time to sit and waste 6 months on a book. If you had that time, that is great, but none of us have that liberty of time. The most important thing in the world is time, right? So that is where follow like a hybrid approach where you do hands-on as well as you learn the concepts. Start off by understanding how to process numeric data, categorical data, how to handle missing values, how to handle outliers, learn a bit about outlier detection systems. Then you go into exploratory analysis. You should know how to use the right visualization for the right kind of data. I've seen people who have done courses from universities or even boot camps, and then if you ask them how to plot this particular feature, they are still confused between when to use a box plot or whatever histogram and so on. So you should be clear about all those things. Then you go into statistics also simultaneously during the EDA step and learn about statistics, descriptive, inferential, then go into machine learning, learn about the models, but also apply them. Otherwise, it will be way too theoretical for you. And that is where you can do some courses. You can read some books, hands-on machine learning with scikit-learn and TensorFlow. That is from O'Reilly. I think the third edition or second edition, probably second edition, is out. Refer to that. That is a good one. Practical Statistics by Data Science for Data Scientists, again from O'Reilly. That is a good book. So use books as reference. Read them or go deeper into them when you need to for specific topics, but otherwise, do hands-on, do some courses, and that'll help you. Once you have built these foundations, then you can go into deep learning, go into computer vision, natural language processing. If you go beforehand, it is not bad, just that you will not get or you will not be able to appreciate it completely, because once you know machine learning, then you will understand that, okay, this is how it is different, this is how it is similar. Okay, so that would be my advice, that it won't happen in one day, but you have to follow a step-by-step process.
Got that, sir. Okay, what would you say are some misconceptions about the AI in the industry?
Misconceptions, there are
As in something
several
that,
of them actually.
yeah,
Yeah,
as in
sorry, go ahead.
something that as in something the people are told and the industry professionals go through every day, the differences between that.
Sure. So one thing you will see is when you are solving your own problems, you are following a definite path. But in the industry, things you will face roadblocks at a lot of steps. The first roadblock itself could be that the business with whom you are working, they have misconception of how AI can be used. For some reason, they have it in their head that we can use AI to magically get that, okay, by this month our sales will increase by X%. So that is where you will have to play a role. Of course, in most cases you won't be alone, but you'll have a team. But you'll have to play a role of not just building the technical solution, but having these discussions with your stakeholders to showcase the realistic outputs of what is possible, what is the realistic possibilities versus, because AI has been extremely hyped up. Okay, a lot of companies are still not completely in sync with how we can use AI effectively. So that is where you will have to have these struggles, or you will have to go through these struggles of not just building the solution, but educating the people who will use the solution in terms of what is possible and not possible. So always have your assumptions about your model in terms of the limitations as well as the advantages clearly highlighted. That is where the metrics become important, like precision, recall. Once you build these models, you can clearly tell them that if you use this model, there could be a high false positive rate. And that is where you have to tie it back to the business. If you have a high false positive rate, how can it cost the business? Because in general they will not care about things like precision recall. You have to make it simple for them. So and those are some things you have to keep in mind, that people usually think that AI is something which is super powerful and it can solve any problem with ease, but it is the total opposite. AI is not powerful by itself. You as humans are making the AI powerful by using the right data and the right model. Okay, so like I said at the beginning of my presentation, machines are stupid. You enable the machines to be intelligent. That is the biggest misconception a lot of companies or even people who are at these high levels have. And it is not their fault. They are experts in running the companies or businesses, but they will get a lot of sales pitches right from different companies that AI can do this or that. Of course, it has a lot of scope, it has a lot of potential, but it has to be used in the right way. So always remember that you will face these roadblocks along the way, and you have to make sure that you come out of them strong.
Okay, sir. So next we have some suggestions of yours that an undergrad pursuing a career in machine learning should take up, what things he should do, which technologies he should learn, what sorts of competitions he should take part in, and projects.
Yeah, I think so. Part of it is similar to the previous questions we discussed, that definitely go through those things step by step and follow a structured learning process, refer to the courses and the books. No need to do thousands of them, but use some definite ones. You will get a pretty good quality from Coursera and elsewhere. Use some of those books as reference, and also make sure that you are doing projects. That is very important. So if you learn about classification, do a project on classification. Maybe do 2 or 3 projects. Do something maybe in the area of finance if you're interested in, maybe in the area of healthcare. So in that way, build relevant projects which have some real world significance. Like we have a lot of common problems, right? Like iris data or whatever, Titanic data and so on. You should pick up data sets which have some real world significance, where you can build a story around it, so that if someone asks you, you can talk about that, right? And so those are some things you can do. Competitions, I will tell again, it depends on whatever other things you're doing. Like don't forget your whatever university or other preparations. But yeah, if you see some machine learning competitions happening, be it Kaggle or elsewhere, you're more than welcome to participate. That will help you improve. If you see some hackathons happening, you can even go for that, because there often you have to build a small scale prototype. So in that way, it also sharpens your coding skills, plus it improves your skills of working in a team. That is very important for the industry. So yeah, those are some things which you can always do. um, and keep improving yourself. That is what I will say. Like, don't stop learning. Yeah.
Okay, sir. Next, we have what what should a student with some experience in ML or deep learning, specifically computer vision in this question, what should he do to get an internship, he or
You have to
she?
seek out companies. A lot of startups are there. Even I know for a fact, even in India, for that matter, there are a lot of computer vision startups which are there. Some of them are even well funded. So you have to go out there, check out LinkedIn, maybe reach out to the founders, or even apply for the job positions which are sometimes there, and seek out the internship. No one is going to do it for you. It is hard, it is not easy, but that is how it is. You have to reach out to them. Some of them will not respond to you, some of them will try to showcase what value you will be adding to them, showcase your skill sets, and talk about that you want to do an internship, you want to gain experience in the real world, and that is how you can get some opportunities. If you see, sometimes they will post on social media, typically maybe sometimes Twitter or LinkedIn, that they are looking for these kind of things. So try to build a network of people also. Often you will see opportunities being posted, so then you can reach out to them. But that is what you have to do. You have to get out there. It's typically easier to get internships in some of these startups because they will be looking for people with real skills who can do work, versus larger companies because the process is a bit more involving. So that is what I would recommend. You get to learn much faster in a startup. Not that bigger companies are bad. If you get an internship opportunity there, you can always go for it. But always check out the job description, and then you can make a call whether it matches what you really want to do.
Definitely, sir. So, startups are known for having a very high growth curve, especially as a intern over there. For next we have from Rohit. He's asking us about your favorite use case of AI in the industry and why.
That's probably a tough one because, like, I like solving a lot of problems, I would say in general. But anything where it has something to do with images or text is typically something I like because it is not super easy. The data usually ends up being multidimensional, so you have to think about a lot of aspects, and you will usually need to end up using some kind of neural network models. So anything to do with natural language processing, very useful. Anything to do with images, very useful. Like, let's say, super resolution. It's a tough problem because you are not just predicting a class or a category, but you are actually predicting a full image. You're generating a full image. So I think generative deep learning is something which is very interesting for me. But coming back to the question, I would say it depends on how much value really I can add to the problem. I would rather solve a problem which is using simple logistic regression, but which gets end up being used right in the future, rather than building a super fancy model, but it never ends up being used. So that would be my thing. And I've solved a lot of problems in manufacturing, in the software side of things, in infrastructure, supply chain. So I mean, in general, I like solving any of these problems, including even like if it's a simple anomaly detection problem. I would like solving it as long as the solution gets used.
Okay, sir. So does performance of model depend on the quality of data or amount of data that it's been trained on?
Yeah, good question. I would say both, honestly. It's not like if you have great quality data and you have like 50 rows of data, it will perform really well. So you do need a decent amount of data. It is hard to say how much data you need because it will vary completely based on the problem. So you really have to try and see, like, okay, if I take 75% of my data set, how does it perform? Maybe cross validation score. If I take 50%, how does it perform? In that way, you can get a feel of how much data might be necessary for you to get a good performance. But the other thing is, of course, if you have millions of records and there is literally no pattern in those problems. Like, let's say you are tracking whether event number 45 and event number 67 are occurring to lead to a failure or not. And for just before failures happen, the same two events happen, and just before a machine is also functioning normally, the same events happen, right? So there is no way of distinguishing then whether a failure is happening or not. So if you have that kind of data where your features are not good, your features are not conclusive to solve the problem, then even if you have 10 records, even if you have a million records, your model will perform horribly. So in that way, the quality of data as well as the relevancy of your data is very important. Amount of data, it depends, like I said. Nowadays, with images, text, and so on, with transfer learning, even if you have less data, you can get a good performance. Doesn't mean like it is a silver bullet that if you have just 10 rows or 20 rows of data, you will always get a good performance. So I would say a combination of both is always useful. Yeah.
Okay, sir. How do we decide which ecosystem is best to master?
Um, it's a hard one to say because it depends on your interests. So I would say go with your interests honestly. Every ecosystem is has its own benefits. If you want to go into machine learning, typically go for Python. If you want to go more into business analytics, you can check out R also. You can do Excel, SQL, right? If you want to be a web developer, probably the Node ecosystem is the best one for you. So yeah, at the end of the day, it really depends on your interests and what you like to do. If you want to build enterprise applications, Java is more used more. So based on that, you can then master that kind of an ecosystem.
Okay, so Shivam from the previous question adds that fog computing is making quite a buzz. How different is it from cloud, and are the libraries and industrial standards the same?
Sure. So it depends. I mean, a lot of things are making a buzz, but yeah, cloud computing. See, cloud is nothing but your data and your compute is in a server. You will send your request to that, it'll do the computation, and then it'll send your response back to you. Any kind of fog or edge and so on computing is where it's typically on device, usually more than often. So the idea is, can we prevent the latency of sending data, sending requests to a distant machine and then do the inference or computation there and then get back the result? Like, let's say self-driving. By the time, if you are doing a self-driving to detect a pedestrian walking in front of you, if you take the snap, right, of the image of the scene right in front of you, send it to the server, process the image, run an object detection model, detect the passenger, send the coordinates back to the car. By the time you do that, it has probably already hit the passenger, right? So that is where you need on device computing. So that is where these technologies are becoming more and more popular, where can we use microcontrollers, can we use microprocessors, and can we put the model on device itself? So that is where Python important, C or C++ also very important. So sometimes you will see those kind of languages become very important because you may need to transform your code into low level language code and then embed it. So yeah, the libraries will be different. I mean, yeah, you have things like TensorFlow or PyTorch, which will help you transform your models into um, usable formats for edge devices, but you may need to learn a bit more of how to interface with those low level devices. And that's where it'll be fairly different and sometimes a bit more challenging than regular data science.
Thank you on that, sir. How can one learn problem solving for this field? This comes from Chavi.
I think your question is your answer. You learn problem solving by picking up data sets out there and solving them at the end of the day. So read a lot of blogs of companies like Netflix, companies like Uber, Microsoft, IBM. They will post a lot of case studies where they talk about how do they, even Google for that matter, they will talk about how do they solve problems in the real world with data science or machine learning. So if you read those blogs, that is your first step to understand that this is how Google used deep learning to build a plant disease detection system for people in Africa. They actually did that, by the way. So in that way, you can learn about the technology, the solutions, the models used. They won't disclose everything, but they will disclose a lot, which is really good in this day and age. Start off there, and then you try out some of those things on your own by using open data sets and trying to build solutions.
Okay. So from Nita, what are the roles slash position freshers are hired by the company for AI and ML jobs?
The most common one is data analyst. It has different forms: data analyst, business intelligence analyst, business intelligence developer. So, all of that has to do with working a bit on the business side, doing some data analysis, visualizations, building dashboards, reports. Not a lot of advanced machine learning there. That is where you have the data scientist role. You can have different levels, again, depending on the company, right? So associate, junior, and so on. And then you have data engineer roles, which is more about pipelining and, like I said, transforming data from one form to another, extract, transform, load, those kind of pipelines. And of course, software engineering and machine learning, or machine learning engineer. So those are the four broad roles I really see: analysts, scientists, engineers. And engineers, you can be data engineer, machine learning engineer.
Okay, sir. Uh, so we have Suraj thanking you for the good vibes.
Yeah, thanks a lot for everyone for spending time for the presentation. Definitely, glad to share my knowledge.
Hmm. Chavi again with the thank you. Hmm.
Sounds good.
Yeah, I think that's about it for the questions, sir.
Great. I think definitely good questions. Thank you for attending the presentation. Hopefully, that gave you some good, real perspective on AI for the industry. And yeah,
Definitely, sir.
that's all from my side.
Yeah. So we're grateful for having you here with us today. Thank you so much for spending your time and sharing your knowledge with us. And I'm sure everyone who was on stream took a lot from this webinar.
Absolutely.
Such a real world insight into the data science and the bleeding edge of technology, which is artificial intelligence, is rare. So thank you so much, sir.
No problem. Thanks a lot, everyone. Thank you for having me here.
Thank you. We'll be ending the stream now.
Thanks. Yeah.